Hello, Gen Chem Nation. Today we are getting into thermochemistry. And thermochemistry is basically, the study of the relationship between chemistry and energy. When we think about energy, we have a couple of notions, right? Energy is basically the capacity to do work. And work is defined as basically a force acting through a distance. So pushing the desk across the room, right, is a notion of work. Energy can also be transferred through the idea of heat. And heat basically is, the flow of energy caused by basically temperature differences. And so those are kind of the two important things to begin with, is this idea of heat and work. We also have these other ideas of kinetic energy, or ideas of energy, such as kinetic energy, right? And so this is, energy associated with motion. And that's, very much tied to thermal energy. Which is basically the energy associated with the temperature of an object. So kinetic energy and thermal energy are very much related to one another. We then have the idea of potential energy. And potential energy is basically, the energy associated with position. Of an object. And that's related to the idea of then chemical energy, which is the energy associated with bonds. Within bonds, of a molecule. And so those are the different types of energy, which all kind of relates to then the law of conservation. Which basically says that energy is neither created nor destroyed it simply flows. So that's some introductory definitions. Um, and with this idea of the conservation of energy, right? It's this idea that we have a system, and the system is then surrounded by the surroundings. And so we have a flow that actually happens. There's a flow back and forth between the system and the surroundings. As chemists, we are interested in the system. Which basically is the chemical reaction. So that's what we're interested in. And so now we can head into, thermodynamics, which is basically, the general study of energy and its interconversion. Or rather, interconversions. And that's, what we just talked about, with that notion of the first law. This is really the first law of thermodynamics. It's really the same thing as the law of conservation of mass, but it's just written a little bit differently, that the total energy of the universe is constant. And so this is just saying that this is the same as the law of conservation of energy. So we have what's known as internal energy, and that's what we're going to start to focus on. Internal energy is given this, capital E, and basically is the sum of all the kinetic and potential energies that compose the system. Or that, to make up the system. This is basically known as a state function. Right, and so a state function means it's really dependent, it's just dependent on the state of the system. Not how it got, not how it arrived at that state. State functions are basically are specified by certain parameters, such as temperature, concentration, pressure, and physical state. So it's dependent on all these different, the state of, an energy within a molecule is dependent on all of these other ideas. What's the temperature, the concentration, the pressure, as well as what is the phase of that particular material. So we could look at, a change in energy as delta E. And we could say that would be just a difference between those two states, the final state and the initial state. And if we looked in terms of, in a reaction, we would find that we could look at that delta E maybe in terms of energy of the products minus energy of the starting materials. So, for instance, if we look at, an example here of a reaction, looking at carbon plus oxygen produces CO2 gas. If we look at energy in terms of going vertically up, we find that our carbon and our oxygen gas are at a higher energy than our product, the CO2 gas. And so we see a decrease in energy. The energy of the starting materials is greater than the energy of the products. So if we were focusing in on the energy of the system, this would actually then be less than zero or negative process. That means in terms of the energy flow, we would be looking at the system, right, giving off energy to the surroundings. So here is our energy flow. It's flowing from the system to the surroundings. And so that's why our delta E for the system is going to be less than zero. But counter to that, our change in energy of the surroundings must be greater than zero, right? Because it's accepting that energy. So there's that kind of flow idea, right? So for the surroundings, it's actually positive, or it's accepting the energy. While on the other side, we have our delta E being negative. And so it's donating the energy, or giving off the energy, however you want to phrase that. So that's going from, one material to the other, but we could just kind of flip that system, if you will, and say, well, what if I want to go the other way? What if I want to go from carbon dioxide to solid carbon and O2 gas? Well, we would have, very much the same type of chart, that now our starting material right, is actually lower in energy, and so we have to add energy to then take it to these new products, the carbon and the oxygen gas. So that means that in terms of our energy, the energy of our products now are greater than the energy of our starting material. And that means that our energy, or our change in energy of the system, must also be greater than zero, must be positive, because of what delta E is equal to. So if we now look at the flow, we're really just looking at the exact opposite process now. We can still have, our system, right? But now the flow is actually going the other way. Right? We have to add energy to get this reaction to happen, to get the system to go forward, and that energy must come from the surroundings. So in this case, my delta E is greater than zero for the system, and so it's positive, and it's accepting the energy. And on the right side, their surroundings, well, for the surroundings, that's actually going to be less than zero because it's giving off that energy. So we have negative because now it's donating the energy. So that's the idea of this first law of thermodynamics as far as going between system and surroundings. Earlier we saw, remember that energy can be exchanged, or can exchange between the system and surroundings through two different ideas, through heat and work. So another way to describe delta E in terms of the system would be equal to Q of the system plus W of the system, where Q of the system is equal to the heat, and W of the system is equal to the work. So those are the two components that make up this type of change in internal energy. Let's first look at work. So remember, work is this idea of force applied over a distance. And in terms of chemistry, the gas phase is the only phase that can do work or have work done on it. This is because gases can compress and expand. So as an example of that, we could maybe look at, my drawings aren't always the best here, but give it a shot. Where here we have basically a cylinder, and at the top of the cylinder here we have a piston. So here is a piston, meaning it can go up and down. And then here we have gas. Remember, gases take up the entire volume of the vessel. So here, just showing you a gas interdispersed. And if we go to the right, and let's say take our image again, I'm just going to kind of cut and paste this over and then do some edits here. Where now what we're going to see is compression actually happening. Well, now our cylinder has the piston now down at the bottom. And so this would be now looking at a compression that's occurring. So we still have our gas in the bottom, but now it is in a much smaller volume. So in this case, in terms of compression, work of the system is positive. Work is being done on the system because we're pushing the piston down and compressing the gas. If we come back the other direction, we are now looking at an expansion. And so now the work of the system is actually negative because it's now pushing up on the surroundings. And if we look at the differences here, we have a change in volume that's actually occurring. If our piston was roughly here, right now it's actually down here. So, we have a volume change, whether compressing or expanding. So in terms of work, we look at it a little bit differently with this idea of a force times a distance, right? So we think about work being that notion of a force, right, applied over a distance. We now take that to force being pressure and distance being a change in volume. So that's how we can look at work in terms of a chemical process or a chemical change. So work is equal to basically plus or minus P delta V. where P stands for our pressure, and delta V would be our V final minus our V initial. So if the system is expanding, then the system is doing work on the surroundings. This means work of the system is equal to a negative. And contrary to that, we don't like to talk too much about the surroundings, but it means that the work of the surroundings would be the opposite sign, would be positive, right? Surroundings accepting that heat or accepting that work. If we can have the opposite scenario, if the system is compressing, then that means the surroundings are doing work on the system. Right? And so this means that the work of the system is equal to positive, and the work of the surroundings would be then negative. So some good terminology there. The system is expanding. The work of the system is negative. It's giving that off, right? If the system is compressing, that means now the system is having work done on it. It's accepting that work, and so now our work is positive. The equation above is pretty general. For basically either the system or surroundings. That's why we see the plus or minus sign. To be specific, the work of the system is equal to negative P delta V. And so that's how we can relate the work of the system. Now, in terms of units, remember energetic units like to be in terms of joules. So there's often a conversion unit involved here. And remember, a joule is a kilogram meter squared per second squared. There are other units, such as calories. I think if we look, there's a conversion. 1 calorie is 4.184 joules. But we focus on joules or kilojoules. So if we think about the work of the system above, in terms of units, we would get atmosphere liters in terms of our units, right? We have here our pressure unit of atmospheres, and we have our volume unit of liters. And so there's a handy conversion for that 1 liter atmosphere is equal to 101.3 joules. This is really an important conversion to remember as Q and delta E are in terms of joules. So we ought to see a conversion there. So we could do a simple example of this idea of just work, focusing on work, but applying it to the notion of a change in energy. So what is the change in energy if a gas expands from 1.32 liters to 1.74 liters at a pressure of 0.35 atmospheres by adding 225 joules of heat? So if I look at what I'm trying to figure out, I'm looking for a change in energy. And if I notice, I see that I have a value of heat. So I have a value of Q. And I know that that equation is Q plus W. And going one step further, I could say that this is Q plus W, where W is negative P delta V. Right? So we're all in terms of the system here. So in looking at the values I have my heat value, right? It's the 225 joules. That is positive, right? Because notice that we are adding 225 joules of heat. We also know our pressure is 0.35 atmospheres. And we have a V final of 1.74 liters and a V initial of 1.32 liters. So really this is just plug and chug. We have the equation, we have all the features of the equation, right? Our changes in volume as far as that expansion is concerned, as well as our pressure as well. So we can just plug these values into our expression and solve. Now here's the problem. Right? If we look, we're going to have different units here. So we have to be very, very careful. Right? Our units aren't going to match up. So we have the 225 joules, and so that's going to be then added to our work, which is a negative 0.147 liter atmospheres. So we can't combine because of different units. And this is the most common mistake students do. They just plug it in and keep going, right? Liter atmospheres needs to get into joules. So if I take that negative 0.147 liter atmospheres and now convert it, in that there are 101.3 joules for every 1 liter atmosphere, that value in terms of work is equal to a negative 14.9 joules. Right? Now I can do the sum. So our delta E of the system would be equal to Q plus our work. And our work is at negative 14.9 joules. And so our change in energy for the system would be equal to 210 joules of energy. So that's how we can look at work as solving for work in terms of a volume change and at a pressure to figure out the change in energy of the system. Notice that the work is negative, and that makes sense because remember it says it expanded. So the sign is correct as far as what we would expect for that actual work value. So now let's get into heat, otherwise known as this little Q. And basically heat is the thermal energy exchange between system and surroundings. This idea of thermal energy always flows from hot to cold. So that's the nature of Q. There's this idea of heat or thermal energy, and it's a flow process like we've been talking about, just like with work, right? We have work of the system, work of the surroundings. We also have heat of the system, heat of the surroundings as well. So if our Q of the system is something that is positive, this means the system is accepting heat from the surroundings. This is also known as a endothermic process. Endothermic, kind of think about it like skeletons. There are endoskeletons and exoskeletons. We have an endoskeleton, or skeletons on the inside of our body. And so if the system is accepting heat, it's like it's internalizing it, much like our skeletal structure is internalized in our body. And so that's known as an endothermic process. We can also have the flip side of that, which is something that's negative. And so now that means that the system is, releasing heat, right, to the surroundings. And so this is also known as an exothermic process. So we have, the negative Q of the system, or we have the positive Q of the system. And if it's negative, that's an exothermic process. If it's positive, well, that's an endothermic process. And just like we had before, right, the Q of the system is equal to the negative Q of the surroundings. And that's that idea of heat flow. Much like we have with the work idea, we have the same thing with heat. And the heat will continue to flow basically until the temperature of the system is then equal to the temperature of the surroundings. So you can imagine, maybe a beaker and that beaker is filled with water. Let's say, the temperature, of the H2O equals 25 degrees Celsius, just, for instance, and we drop in a brick of iron. Right? And the temperature of the iron is, let's just say 80 degrees Celsius. Right? We're obviously going to have heat flow that's occurring. And we're going to have heat, emanating from the iron. So the iron will, cool down, right? While the water will heat up. And that's that idea of, thermal flow. Eventually, could end up with the the kind of the same setup here as far as our beaker with the water with the iron in it, but now they're going to actually be the same temperature eventually, right? So here we have again those purple arrows showing heat flow, right? Iron would have a Q that is equal to something that's negative, right? Because it's cooling down, while the H2O, its Q would be something that's positive. It's actually heating up. And so that continues until eventually they reach the same temperature. So the temperature of your H2O is now equal to the temperature of the solid iron. So that's this idea of thermal equilibrium. So when the temperatures are equal, meaning the system temperature is equal to the surroundings temperature, then basically you are at thermal equilibrium. So that's the notion of Q and heat flow. So, and this is something I think that we all kind of know, we just never have really thought about quantifying it. So now let's get into quantifying heat flow. And in quantifying heat flow, we have two things that we have to understand. Both are related to one another. And one is known as specific heat capacity. The other one is known as a general heat capacity. But let's first start with the specific idea. Specific heat capacity is basically the amount of thermal energy, right, or joules, that needs to be given to 1 gram of a molecule or element basically in order to raise the temperature of that molecule or element 1 degrees Celsius. Specific heat capacity is equal to C sub S, and it has units of joules per gram degrees Celsius. And so this is specifically, just saying, how much, heat is required to, say, if I have a gram block of aluminum, how much heat do I need to add to it to increase its temperature by 1 degree Celsius. Specific heat is specific to the molecule or element and the phase of the molecule or element. So, for instance, if we look at like water, specific heat for water is 4.18 joules per gram degree Celsius, while the specific heat of H2O in the gaseous phase is 1.84 joules per gram degree Celsius. So these are specific to the phase of the molecule as well. So often, you have to look up the specific heat capacity. So in terms of relating it to Q, in terms of energy flow, Q is equal to mc delta T when we talk about specific heat capacity. So here we have our heat, and we be in units of joules. We then have our mass, which we're going to be in terms of grams. We have our specific heat capacity, right, and that's in joules per gram degree Celsius. And then lastly, we have our delta T, which is T final minus T initial, and that would have to be degrees Celsius according to our specific heat capacity constant. So that's how we can actually measure, the heat, required or the heat given off, right? That really depends on T final and T initial for a particular mass of a molecule or element, and then how that relates to its actual specific heat capacity. So that's one way to measure heat flow in terms of something very specific. So let's take a look at an example of this idea of thermal equilibrium. So we have an aluminum cube here at 45.8 degrees Celsius is submerged into 105.3 grams of H2O, and that water is at 15.4 degrees Celsius. If the final temperature of the H2O is 17.3 degrees Celsius, what is the mass of the aluminum cube? So here we have basically a very good example of thermal equilibrium, right? We have two different states here, if you will. We have an aluminum cube, and we could say that the Q of the aluminum solid, we could say is, I don't know, the system. And then we have this idea that it's submerged into H2O. So there's a Q of the water as well, which we could call, the surroundings. So this is that picture that we had earlier, right, with the hot iron cube or iron block going into the water. And so we're going to have this thermal equilibrium where the hot aluminum cube, in this case, is giving off heat to the H2O. And we get that from that different temperature idea. If we look at where we're going, we are looking for this mass of the aluminum cube. And so putting this all together, we have two different ideas then of Q. We can talk about Q in terms of the aluminum, which would be, the mass of that aluminum times the specific heat capacity for that aluminum times then delta T. And we have the same thing going for the H2O. We have a mass of the H2O. We can look up, just like with the aluminum, the specific heat capacity for the H2O. And we also have a delta T. An important thing to realize is that the T, final for the aluminum is going to be equal to the T final for the H2O. Right? That's that thermal equilibrium idea, that the hot aluminum brick will give off heat, the water will accept that heat, and it will do so until the temperatures are actually the same. And that's that notion of thermal energy transfer. So scrolling back up, just to look at the question, we have components for the aluminum. Namely, we know our temperature initial. For the water, we have our mass of the water, and we also have our temperature initial. And then we have the temperature final, which, remember, is going to be equal for both. So even though it says the final temperature of water is this, realize that, both of them have to be exactly the same temperature. So in just, kind of writing those values below, right, we have the temperature initial of 45.8 degrees Celsius for the aluminum. We look up the specific heat capacity for the aluminum. It has a specific heat capacity of 0.903 joules per gram degrees Celsius. And if we go to the other side of the heat flow, we have a temperature initial for our H2O to be equal to that 15.4 degrees Celsius. We have a mass of the H2O as at 105.3. And we have a specific heat capacity. We'd have to just look this up. For our water to be 4.18 joules per gram degrees Celsius. So we had the ability to set these two together, and so what we have to understand, right, is that Q of the system is really equal to Q of the surroundings, right? We just need to have, a negative sign in order to show the heat flow. Doesn't matter what you call the system or what you call the surroundings. So I'm going to call the aluminum the system, and I'm going to call the H2O the surroundings. So if I plug those two in, it would start to look like this, right? We have the mass of our aluminum times the specific heat capacity of our aluminum times its change in temperature. And so that's going to be equal to the mass of the water times its specific heat capacity times its change in temperature. So if we start to plug in the values, we really have everything. You don't have the mass of the aluminum, but that's what we're looking for. The specific heat capacity for the aluminum is 0.903. Joules per gram degrees Celsius. Our T final was the 17.3 degrees Celsius. Minus then our temperature initial, which is the 45.8 degrees Celsius. And so that's going to be equal to the negative of now the water portion of the expression. And I apologize for our equation above here. We should have that, negative portion out in front in terms of that relationship, right? Q is equal to negative Q. So now we can plug in the rest. We have our mass, right, the 105.3. Our specific heat capacity of 4.18 joules per gram degree Celsius. And then we have our temperature of 17.3 degrees Celsius minus then that initial temperature of 15.4. If we take the product then of both sides, we take the 0.903 and multiply through, we would end up with a negative 25.7355 joules per gram. And on the other side, if we multiply through everything, we would have 836.2926 joules. And we still have that negative sign out in front. So our mass of that aluminum solid would be equal to the negative 836.2926 joules divided by the negative 25.7355 joules per gram, and we end up with a value of 32.4956 grams of that aluminum. And if we look back, it's really 3 sig figs where we should have this. So we could also say, 32.5 grams. So that is our final answer for that. So that's an idea of thermal energy transfer. in terms of something hot, something cold. Remember, heat flow goes from that hot object to the cold object. But as long as you have the Q is equal to negative Q idea, you don't really have to conceptualize that heat flow. You just realize that, okay, one side has to be negative, one side has to be positive, and that will all work out in terms of a calculational feature.